Atish is actually now the director of the ICTP. And I'll send in chat his slides, which he, in case that's a convenient way to view it. So Atish, thank you.
Okay, thanks, Ken. It's nice to be back, as they say. I was on Zoom like 2 hours ago. But, it's nice to see so many people from all over the world. So what I would like to talk about are 3 avatars of Mach modularity. So these are the 3 avatars of Mach modularity. And this is, and the 3 avatars are basically holography, topology, and duality. And it's based on this work that I've been doing for the last few years with a number of people. And these are the 3 papers which sort of deal with these 3 avatars. And these are the collaborators, Samir Murthy, Ran Zagier, Diksha, who is a student, Arnab Rudra, who's postdoc at ICTP, Vitan, and Putrov, who is now a faculty at ICTP. So, so in Ramanujan's famous last letter to Hardy in 1920, he gave examples of Mach theta functions. And of course, being Ramanujan, he gave no definition, for which he found very interesting hints of modularity. And the typical function that he wrote down is something like this, which to an untrained eye looks like just some hypergeometric function. But Ramanujan saw some hints of modularity. And despite a lot of work by many eminent mathematicians, this fascinating hidden modular symmetry, it remained mysterious for over a century, or close to a century, until the thesis of Zweigers in 2002. And the basic idea of, so I'm sort of going to give a bit of an introduction to Mach. I mean, I think not everybody here is familiar with Mach theta functions, I'm assuming, and not everybody is familiar with all these different aspects. So I'm going to give a kind of a introduction to the whole field a little bit, so that to put it in a context of, and not everybody has followed this. So this Mach theta function was difficult to characterize, is because it's almost modular. And so it's a bit difficult in much the same way that a figure is, if you say it's almost circular, it's hard to give a definition, because then does it have a little blip on the left or a square on the right? You don't know. So let me just briefly remind you what modular forms are. A modular form is of weight k on SL to Z, is a holomorphic function on the upper half plane, and which has nice, basically is invariant under a modular transformation, if you take out this factor of c tau plus d to the minus k. And in particular, it's invariant under translation. So you can do its Fourier expansion, the Q expansion. And the Q coefficients basically summarize the modular form. And modularity already appears, before going to Mach modularity, already appears in physics in these 3 avatars. In holography, in ADS3 quantum gravity, the modular group SL2Z appears as the group of boundary global diffeomorphisms of the ADS3, the Euclidean ADS3. In duality, the 4-dimensional quantum gauge theories have S-duality group, which is a congruent subgroup of SL2Z. And in topology, if you're computing the elliptic genus of some 2-dimensional conformal field theory, then the SL2Z is the mapping class group of the torus on which you're computing the partition function. And physical observables in all these 3 physical contexts are expected to exhibit modular behavior. And the reason modular symmetry has been so powerful, I mean, has had a lot of impact in physics, is because modular forms are highly symmetric functions. And it is sort of summarized, this power is summarized by this theorem, that the ring of modular forms is generated by just 2 functions, 2 Eisenstein series, E4 of tau and E6 of tau. And then you can generate any other modular form of any given weight just by multiplying them and adding them. So for example, if you want a weight 12 form, then it can only be E4 cube, because when you multiply, the modular weight adds. So it can only be E4 cube or E6 square. And then all that you have to determine are the coefficients A and B. So therefore, if you look at its Q expansion, which looks like infinite number of Q coefficients, AN, you just have to fix a couple of them, the first one. And if you know that the function is modular, so you reduce this kind of an infinite number of Q coefficients to just a few, and it becomes a finite problem. So it's enough to know the first few Fourier coefficients to determine the modular forms completely. And this is sort of many times, if you look, is behind all these kind of magical identities that mathematicians like Ramanujan wrote down. Because if you have in your mind some notion of modularity, then you just have to compare the first few coefficients, and then you know that the two sides are equal, even though they look completely different. And then second reason why modular symmetry is very powerful is because it relates F tau to F minus 1 upon tau. And this means it relates high temperature to low temperature in a 2D CFT, or strong coupling to weak coupling in a gauge theory. And this leads to the Cardy formula, or this very beautiful Hardy-Ramanujan-Rademacher expansion, which is a exact convergent expansion of the analytic, so sort of this analytic number theory that expresses all these coefficients an in terms of some Bessel functions and things like that, and as an exact convergent expansion. So that also has been very useful using Cardy formula in statistical mechanics, and like the Hardy-Ramanujan formula, for example, if you're interested in quantum entropy of black holes going beyond the Bekenstein formula, then this is the thing that you use. So therefore, having this kind of an exact expansion is very powerful to really control the quantum corrections to the quantum entropy of black holes. So now let's come to mock modular forms. So now the modern, of course, Ramanujan didn't give a definition, but with the work of Zwegers and as explained by Zagier, the definition of a mock modular form involves a pair, f and g, where f of tau is a holomorphic function with some nice properties, doesn't grow too much at the cusp, etc. And g of tau is a holomorphic modular form of weight k minus, sorry, I cannot see my own notes. Sorry. Okay, good. And the main point is that g tau is a holomorphic modular form, but f tau is not a modular form. However, you can add to f tau some non-holomorphic corrections constructed out of g tau, which we will call g star of tau and tau bar, such that this function f hat then has nice modular properties. It transforms like a holomorphic modular form of half integer weight of some congruent subgroup of SL to Z. So basically, this is this kind of incompatibility that you can see, that f is a mock modular form which is holomorphic, but it's not modular. G is called its shadow, and it is holomorphic and modular. And f hat is this modular completion, which is not holomorphic, but it is modular. And f hat, in a sense, contains all the information, but it is not holomorphic. So that's the kind of essence of mock modularity. It's like the exclusive OR. It's holomorphic Xor modular. The function f is holomorphic but not modular, and the function f hat is modular but not holomorphic. And for some physics applications, f is the right object that you want to look at. For example, for counting, you want some Q coefficients. Whereas if you're looking at the some duality symmetries or SL to Z symmetries, then f hat is the more natural object. And this incompatibility between holomorphy and modularity, that is the essence of mock modularity. So are there any questions at this point? Okay. So how do you characterize this lack of holomorphy? So you can take this function f hat and you take this non-holomorphic derivative like del f hat by del tau bar, and you multiply by some factors which depend on the weight. And then you get the shadow. So in that sense, if from f hat you can recover everything. You can look at its holomorphic part, that is f, and you take the holomorphic anomaly equation, and it will give you g of tau bar. Okay. And the shadow, even though it is both holomorphic and modular, it does not by itself determine the modular completion, because you can always add to f hat any modular form of the right weight, and it would not change this holomorphic anomaly equation. Now, even though G is holomorphic, the non-holomorphic correction G star is not holomorphic and it's not modular. And the holomorphic mock modular form by itself is not modular. The completion is modular but not holomorphic. Okay. Now, this G star can be actually constructed very explicitly, knowing G. So, if G has a Q expansion in terms of some coefficient Bn Qn, then G star has a very explicit formula given in terms of B naught and this Bn times this incomplete gamma function, 1 minus, this incomplete gamma function, if you recall, is defined like this. It's related to the error function and things like that. So, and this incomplete gamma function actually appears all over the place in this story. It appears also in the Atish-Singer index theorem, Atish-Singer-Patodi index theorem. And it will appear in the mock, it appears in the mock modular story. And it will make its appearance in our calculations in quantum field theory. And that is sort of the connection. This incomplete gamma function is what will connect all these things and exhibit the mock modularity. So as I said, to summarize the mock modularity, it's like having suppose you have holomorphy as one of your requirements and modularity is one of your requirements. Then a nice holomorphic modular form is like a blue circle. Whereas what we have here, we don't have a blue circle. We have a blue circle with a little bit of red, which is the G star. And then it looks circular, but then it's no longer blue. And however, the red part, which is G star, can actually be constructed out of another blue circle. So mock modular form, I had to explain this to some popular press, and this is how I explained it, that it's like a, it's not easy to describe because it is not, the symmetry properties are kind of more complicated. Now, another object that we will actually be dealing with are Jacobi forms. And they are, some slight one-step generalization of the ordinary modular forms. And they are basically functions of two variables instead of one variable on the upper half plane and the complex plane. And it's a Jacobi form of weight k and index m. Now it is characterized by two integers, k and m, which is modular in tau and elliptic in z. So roughly speaking, what it means that it's symmetric, it's invariant under modular symmetry, up to some phases. And it is invariant under double translations on a torus. So it's doubly periodic again, of course, up to a phase, because you cannot just have a doubly periodic function. So these are the more explicit properties of this. So it's elliptic, which means it's doubly periodic, and it's modular means it's roughly doesn't change under modularity. And once again, using these two properties, you can have a Q expansion because it's now shift symmetric both in tau and z. And it is summarized by Fourier coefficients, which are C and R, Q to the N, Y to the R, where Y is e to the 2 pi I z. And Q, if you remember, is e to the 2 pi I tau. So you should think of these shifts, Z going to Z plus lambda tau plus mu. Think of Z as a coordinate on a torus whose complex structure parameter is tau. So you think of the torus as a lattice on the complex plane, modded out by a lattice. Think of a torus as complex plane modded out by a lattice with the complex structure parameter tau. Then what you are saying is that this function is well defined, roughly speaking, up to phases, and you can pull it back. Okay, so that's the definition of a Jacobi form. And as I'm sure most of you know, that elliptic genera is where the Jacobi forms appear. So if we take a conformally invariant nonlinear sigma model with some target space with 2, 2 super conformal symmetry, then it has a right moving super Virasoro algebra. And you can define the elliptic genus by this function chi tau of z, which is a trace over basically if you think of e to the 2 pi I tau minus e to the 2 pi I tau bar as the temperature, then it's like a trace with some twist. And such an object is actually, for a compact conformal field theory, is the Jacobi form. And this you can show fairly easily. But the important point is that it does not depend on tau bar. Because a priori, the definition, if you look at it, it has on the right-hand side a dependence on tau bar, because it's exponential of minus 2 pi I tau bar h right, whereas the left-hand side, I'm showing only tau. And the reason for that is Witten's famous argument that the right moving theory is supersymmetric, and therefore bosons and fermions are paired. And so if you have any bosonic state, it is paired with another fermionic state. And therefore, if you're computing a trace -1 to the f right, which is the fermion number, then they will cancel in pairs. They don't cancel in pairs on the left-hand side because you're sort of adding this e to the 2 pi I z f left for the left movers. And so what it is counting are the right moving ground states with arbitrary left moving oscillations. And this is something that we have encountered a lot of times, for example, in the black hole story with the Strominger-Waffa string. You're interested in computing the right moving ground states with arbitrary left moving oscillations. Think of a string which only has left moving oscillations. And that is protected by supersymmetry. And that's why it's a very interesting topological quantity. And this is where topology enters into the story. And the conformal symmetry is kind of obvious because if you write this as a path integral, then a path integral, if you use a diffeomorphism invariant regulator like a heat kernel or something like that, and because you have a while invariance of the conformal symmetry, then it's easy to see that the path integral has to be modular invariant because modular symmetry is basically diffeomorphisms modulo, global diffeomorphisms modulo while symmetry. And similarly, using the fact that you have a spectral flow symmetry, you have a U1 current and the spectral flow symmetry, you can show that it has elliptic properties. So both the modular property and elliptic properties of the mathematically that we needed for the definition of the Jacobi form arise very naturally when you define this object, which is elliptic genus, and which is a very natural object to consider as some kind of a indexed partition function. And once again, so a couple of examples of Jacobi forms that we are all familiar with would be, first of all, the elliptic genus of K3, which I'll go down first. Elliptic genus of K3 of weight 0 and it's a Jacobi form of weight 0 and index 1. And it has a very explicit expression. I'm denoting it by b tau of z in terms of the Jacobi standard Jacobi theta functions. So it's basically it should be theta 2 square, theta 3 square, and sorry, I just copied wrong. So it should be theta 2 square tau z divided by theta 2 square tau plus theta 3 square tau z divided by theta 3 square tau plus theta 4 square tau z divided by theta 4 square tau. And these are all the, these are the theta functions which don't vanish at z is equal to 0. And eta is the Dedekind eta function. And similarly, if you, instead of, so basically if your target space superconformal field theory had a target space K3, then this is the elliptic genus that you would get. And similarly, you could take the target space to be T4, and then it is given by theta 1 square tau z times divided by eta to the 6 tau. And once again, heuristically is very easy to understand. If you look at the eta to the 6 tau, there are 4 factors of product over 1 minus q to the n. And those come from the 4 bosons of the T4. And the factor on the top, if you write it out, it comes from the 4 fermions. So it's kind of a, if you write the product representation of the theta function and the eta function, it's very easy to see that this is nothing but just 4 free fermions and 4 free bosons. So it's a very easy object to compute in physics. And it appears very naturally in the theory of Jacobi forms, because once again, using the symmetries, the power of Jacobi forms and power of modularity is that once again, there is a theorem by Eichler and Zagier. The ring of Jacobi forms is generated by just these 2 functions. So just like the modular forms were generated by E4 and E6, meaning that you could just write down any modular form of any given weight in terms of some small number of combinations of these 2 and powers and multiply. Similarly here, given A tau and B tau, you can write down, and ordinary modular forms as coefficients, you can write down any Jacobi form. So this is very powerful. For example, if you want weight 4 index 2 Jacobi form, then there are 2 possibilities, because A has index 1 and B has index 1. So the only way you can get index 2 object is a square and b square. But then a square has weight -4 and b square has weight 0. So if you want something of weight 4, you have to use this combination with some coefficients a and b. So once again, it's a very powerful symmetry like a circle that once you determine a couple of Fourier coefficients, you have determined the Jacobi form completely. Now,
Atish, what about A times B?
A times B. A times B could also be a possibility. Sorry. Okay. So you can have one more coefficient, A, C. Yes, that's a possibility. I agree. So with 3 coefficients in this case, you would determine the form completely. Now, another thing is that the Jacobi forms are actually equivalent to vector valued modular forms. So what does it mean? That using the elliptic properties, the fact that you are sort of doubly periodic, you can more or less remove the entire Z dependence from the picture by using the standard level m theta functions. And the standard level m theta functions, if you recall, are just defined by this equation. Theta ml tau z is q to the power l plus 2 mn, etc. So these are like theta functions, just q square, q to the n square kind of functions divided by 4m plus some y dependence. And then, as you can see in the first equation, any Jacobi function on the right, Jacobi form on the right, left-hand side. On the right-hand side, the theta, once you remove the theta functions, it just depends on 2m ordinary modular forms, HL of tau, where L goes from 0 to 2m, sorry, 1 to 2m. And just by looking at the weights, because the theta function has weight half, you get vector valued modular forms of weight k minus half. So there is a kind of one-to-one correspondence between Jacobi forms and vector valued modular forms. So this is the mathematics of mock, sorry, I have introduced mock modular forms. You can similarly define mock Jacobi forms, and I will come to that later. So far I have introduced modular forms, Jacobi forms, and mock modular forms. And you're all familiar with the uses of modular forms and Jacobi forms in physics. And perhaps you're less familiar with the uses of mock modular forms in physics. And okay, some of you I'm sure are, but okay, not everybody here. And that is what I will now turn to. So I have sort of finished the definitions, and now I'll come to the, if there are any questions. So very nice. So, you know, coming from India, actually Ramanujan was always an inspiring figure. And I remember this quote, Freeman Dyson, and you know, I was a student at that time actually, and Freeman Dyson had this very wonderful, if you get a chance, it's a very nice essay called A Walk Through Ramanujan's Garden. It says that my dream is that I will live to see the day when our young physicists, and you know, I was young at that time actually, struggling to bring the predictions of superstring theory into correspondence with the facts of nature, will be led to enlarge their analytic machinery to include not only theta functions, but mock theta functions. And okay, you can read this. And he also says that when the purely mathematical exploration also will have to be done, we'll have to understand the symmetries better. And he was actually quite right about that, because it took several years before the modular symmetries were properly understood from a mathematical point of view. And, you know, but I never really thought that in my research I will really ever come across. They look very curious, but I was sort of forced into it. And as you will see that if you somehow follow the logic in number of physical problems, you are sort of forced into this Ramanujan's garden of mock modular forms. So one of the puzzles that I was wondering about in Paris, actually this was a meeting which Boris and I had organized, and I think Greg was present at that meeting. And there was a puzzle in the black hole story that counting function for the degeneration of quarter BPS black holes for say type 2 compactified on K3 cross T2 is given by this meromorphic Jacobi form, which in terms of the objects that I've introduced looks like b to the power m plus 1 divided by eta to the 24 of tau divided by a tau of z. Now remember, a tau of z was this theta function, theta 1, which vanishes. It has a double zero actually. Theta function vanishes, so theta 1 square actually has a double zero. And if you put it in the denominator, then it has a double pole. And this looked like a kind of a little curiosity, and I was kind of bothered by it. Because the quantum degeneracies for the problem that I was interested in are given by the Fourier coefficients of this counting function. But now if you have a pole, then it would seem that your counting problem is not really solved, because depending on which, and this actually occurs in this famous DVV formula, and that was also criticized for similar reasons, that okay, formula couldn't quite be right, and it turned out that in the end it was right, but for subtle reasons. And given the double pole, the Fourier coefficient would depend on the choice of the contour, and they're not uniquely defined. So the problem was, what is wrong with the counting? There was a puzzle with, there was a second puzzle. So I'm now going to tell you the 3 avatars and 3 puzzles, in which this is how I got into this. Another puzzle is that if you look at the Waffa-Witten partition function for n equal to 4-dimensional supersymmetric gauge theorems on a manifold like CP2, with this coupling constant tau, then there is a twisted supercharge. You can twist this theory, and this is a Waffa-Witten partition function, and the twisted supercharge squares to 0. I mean, that is the idea of the twisting. And you can use that as like a BRS test, like a cohomology. You can define its cohomology. And by general arguments, the partition function is supposed to be holomorphic, because d by d tau bar of the partition function is q of something, and then therefore it is 0. And if you now calculate the holomorphic partition function, then it receives contributions only from instantons, but it doesn't have any nice modular properties as expected from S-duality. And this was actually a puzzle. And in fact, Waffa-Witten, they wrote this paper on strong coupling tests of S-duality. And it seemed to work very nicely for many other manifolds. But here, either there is something wrong with this argument, or there is something wrong with S-duality. So in the black hole context, there was something wrong with the counting of, so there was a problem with the Bekenstein-Hawking formula being statistically explained. And here there was a problem with the duality symmetry. The third puzzle with the elliptic genus is that the elliptic genus of a sigma model is expected to be holomorphic for the reasons that I gave you, because it's like a right-moving Witten index. But for a non-compact SCFT, and people had several examples, like sigma model of an infinite cigar, the holomorphic function is actually not modular as expected from conformal invariance. The question becomes, what is wrong with conformal invariance? And the answer to all these questions involves mock modularity from the mathematical point of view. And this is how I got into it. But then the question was, how do you understand it from a physical point of view? And that was what was sort of has been the interest in my recent work. So, and the answer is that in all these cases, there is a non-compact path integral involved from a physical point of view. So mock modularity gets very nicely related to the physical property of non-compactness of a path integral. And in the black hole story, I will very quickly summarize it, just the relevant part. That there's a very nice story, and maybe not all of you have seen it, that the reason that there is this ambiguity in the counting is because there is a wall crossing phenomena. And in fact, actually, the degeneracies are not well defined. In the physics tells you that the degeneracy should not be well defined for a black hole, because the moduli space of the theory is divided into chambers, and in one chamber the degeneracies are something, and in another chamber they are something else. And so you can, when you cross the wall in the moduli space, the degeneracy should actually jump. So the fact which was a kind of was a problem becomes a virtue. And when you cross a pole, you're crossing a wall, and the residue at the pole is what is the jump in the degeneracy. So this sort of explains why the Fourier coefficients were not well defined. I mean, the fact that they were not well defined was good because it actually corresponds to this physical fact. But that raises another question: how come? I mean, if you are interested in quantum black holes, and that was what my interest was, that because the quantum degeneracy of a black hole is entirely a property of its horizon. I mean, that's why we believe that you are learning something about the quantum structure of gravity, and it should not depend on the asymptotic moduli. So this actually poses a puzzle. And the answer to that question is also very nice. It's related to multi-centered black holes. That the reason you have this jump in degeneracy is that on one side of the wall, you only have single-centered black holes. On another side of the wall, you have the single-centered black holes and the multi-centered black holes. And as you expect from your intuition about quantum gravity or holography, indeed the degeneracy of a black hole is purely a property of the horizon and not of the moduli. But on the right, as you try to cross the wall to the left, this multi-centered configuration can sort of, the distance between them starts to increase, and they are no longer bound to each other, and they drop out of the picture. And that is the reason. So even though the horizon degrees of freedom do not change, the counting changes because of the fact that the multi-centered black holes may or may not exist in every chamber. So what counts? So the question now becomes, what is that object that counts the horizon degrees of freedom related to quantum gravity? And this was the problem that I got interested in. And in this 2007 conference, actually, Don Zagier, actually Boris and I invited him because we were both using his book with Eichler. So we thought that, okay, maybe it's a good way to interact with mathematicians. And it turned out to be a very fruitful interaction, because I remember just sitting in a cafe and I was bothered by this poll. And I said to Don, you know, it's some poll, can we help it? And I thought it's going to be a simple answer, but Don Zagier told me, no, this is a very deep problem in mathematics. Actually, my graduate student only recently solved this, 2002, and it's related to Ramanujan's mock theta functions in some way. So I said, okay, great. So let's collaborate. And we thought we will get done in maybe a few months. But it actually take several years, because even the theory of mock theta functions was not fully developed. So we were sort of part of the development. But the final answer from the physics point of view is actually very nice and simple. The counting function that I showed you has a very nice natural decomposition in terms of a polar part and a finite part. The polar part is called the Appel-Lurk sum, and it is given, it has exactly the same poles as the left-hand side. So basically what you're doing is that removing all the poles. And then you're left with a finite part which no longer has any poles in Z. And therefore its Fourier coefficients are uniquely defined without any ambiguity. So it's therefore natural that you will identify psi m polar to be the object which counts the single-centered degeneracies. So this is a very nice explanation of this fact, a mathematical statement of this fact, that the counting function is the sum of two objects. One counts the single-centered black holes, the other counts the multi-centered black holes. And all the ambiguity of the Fourier coefficients is only in the multi-centered black holes. Of course, as this stands, that's kind of a very trivial statement, because you can always take a function and divide it into two functions. That doesn't require the kind of a glorious title of a theorem. The non-trivial part of the theorem is that, so this is the physical interpretation. Let me first describe that. That psi mp counts the single-centered black holes and psi mf counts the multi-centered black holes. The non-trivial part of the theorem is that both these terms admit a modular completion. So the Appel-Lurk sum is defined in this way. So you can more or less remove, there is some overall factor with some multiplicative coefficient and eta to the 20^4 tau. If you remove that, you are left with this object calligraphic A to M. So let me just remind you, we started with some counting function, psi m, and out of that counting function, which had weight -10 and index m, we split it into two objects, which were again denoted by this index m, but they had some information about the weight, which was -10. And if I remove this eta to the 24 tau, which has weight -12, you are left with an object which has weight 2 and index m. Now, weight 2 really has much meaning in that it's not really a modular function. It doesn't have any modular properties a priori. But the index is a well-defined notion in that it still has elliptic symmetries. So it behaves like a Jacobi form. It has elliptic symmetries of a Jacobi form, but it doesn't have the modular properties of a Jacobi form. And modular completion, similarly, you can remove this factor of P24m plus 1 divided by eta to the 24, and then you are left with phi 2mf. And that we claimed in the DNZ paper, this paper with Murthy and Zagier, that is a mock Jacobi form. It's a new mathematical object that we introduced of weight 2 and index m, which admits a modular completion, which we in much the same way that a modular form admits a modular completion f hat, we called it phi hat of f2m. One can similarly define a modular completion a hat. Both completions are non-holomorphic in tau, but transform as a proper Jacobi form of weight 2 and index m. So this is very similar to what happens with mock modular forms, which depended only on one variable, tau. Here you have a generalization which depends now on two variables. So you have a mock Jacobi form, and it has similar kind of properties that somehow there is a conflict between holomorphy and modularity. So mock Jacobi form, therefore I will define it like this, that using the elliptic property, one can always obtain a theta decomposition like this. So if you have a mock Jacobi form phi 2m of weight 2 and index m, then you can decompose it in this manner using the theta functions. But now HL of tau are no longer modular, but they are mock modular. So this makes contact with my definition of mock modular forms earlier. And this also how you make contact with Ramanujan's mock theta functions. So the mock Jacobi forms essentially contain the same information as a vector valued mock modular form. And the vector valued mock modular form is defined in the manner that I defined earlier, that it is given in terms of some modular, non-modular but holomorphic object, add to it a non-holomorphic correction GL of tau, such that the resulting function h hat has transforms as the weight 3 of modular form. But of course, because it is non-holomorphic, it has a holomorphic anomaly. So once again, this is a kind of an incompatibility table, this holomorphy exclusive or modularity. We had several objects. Let me now remind you. Our black hole degeneracy function was psi, and it was a meromorphic Jacobi form because it had this function a in the denominator, so it had a pole in z. And we could not define its Fourier coefficient well, properly. Then we defined, using the decomposition theorem, a polar part, or by removing some extraneous factors, we defined a mock Jacobi form phi, and then we defined an Appel-Lurk sum which corresponds to the multi-centered black holes A, and we defined a completion phi hat. And now we have four properties. It can be either holomorphic, modular, or it can be pole-free, or it can be simple in some sense. So the meromorphic Jacobi form is holomorphic and modular, but it has poles in Z, so it's not pole-free, and it's definitely not simple because it's telling you the black hole degeneracies. The mock Jacobi form is holomorphic but not modular. It is pole-free because you can define it's a single-centered degeneracies. So its Fourier coefficients are properly defined, but it is not simple. The Appel-Lurk sum is actually basically defined by taking the pole of this meromorphic Jacobi form and taking some kind of an elliptic average by using method of images, roughly speaking. So you're just taking 1 upon z square and taking its average. So you take all the images of z in the upper complex plane and then you sum it up. That was, if you look at the definition of the Appel-Lurk sum, that's what it is. So it's very simple. It's constructed out of just a single pole. And it is holomorphic explicitly, but it is not modular and it is not pole-free. Whereas the completion is holomorphic, not holomorphic and not simple, but it's modular and it's pole-free.
Atish, question?
Sorry? Yes.
Question. Atish, I have a question about your table.
Yes.
So the first column probably should be meromorphic, not holomorphic?
No, by holomorphic, I mean holomorphic in tau.
Yeah.
Sorry, it's meromorphic in Z, but holomorphic in tau.
Okay. And the last column, simple is in the non-technical sense?
Yes, simple in the non-technical sense that the Appel-Lurk sum is more or less determined completely by knowing 1 upon z square. Appel-Lurk sum is basically 1 upon z square with average.
Simple is a relative term.
Yeah, simple is a relative term.
Sorry, do you mind if I ask you the statement of the theorem again? I've often found it difficult to parse, and this is helpful for me.
The statement of the theorem is that a meromorphic Jacobi form admits a unique decomposition in terms of an Appel-Lurk sum and a mock Jacobi form.
I see. So in other words, if you subtract out the Appel-Lurk sum, which is given by the elliptic average of the polar part, and the resulting finite part is mock Jacobi. That's the statement.
Exactly. And this was noticed by Appel and Lerck, and they were, and by Zagier and various mathematicians over the years. And essentially, Zweger sort of unified this whole picture.
One thing that always confused me is the statement of unique decomposition here, because by definition, the polar part is the Appel-Lerch sum, which is given as the elliptic average of the polar parts. So yes, of course, it's unique.
Yeah. So I mean, okay, you can remove the word unique. It admits the decomposition, you can even say.
Yes. And
I mean, unique is, yeah, it's trivially unique.
the other thing that's often, it's not confused me, I've just wondered, but everything else in this talk, the Mach modular forms, the Mach Jacobi forms, Meromorphic Jacobi forms, have been very kind of beautiful objects defined by their symmetry properties. But this Appel-Lerch sum is just defined as, like, here's a function, I'm writing it down.
Yes.
Kind of more beautiful way to characterize this Appel-Lerch sum rather than just here's a function.
Yeah, I think the utility of Appel-Lerch sum is exactly this heuristic notion of the fact that it is simple. Meaning Appel and Lerck discovered that it behaves, I mean, the point is that another way to put it is that you could sort of correct the lack of modularity by, I mean, you could work backwards, and if you sacrifice Mach modularity, if you sacrifice meromorphy, if you're allowed to live with a meromorphic function, then you can, the left-hand side is actually modular, you see.
Yeah, sure. Okay, so it's necessarily, as Craig was saying, kind of a non-technical notion. Okay.
Yeah, it's a non-technical notion. Yeah, so they sort of Appel and Lerck, I will come to that in a moment, because basically Appel-Lerch sum will also admit a modular completion, and the modular completions are, they will both have a modular anomaly in tau, and they are related. And that's why you can add and subtract the modular completion, and then it will cancel out for the meromorphic guy. So what I'm saying is that if you can construct, let's see, sorry, let me not, here. You can construct psi m hat and psi m f hat by the following process. That psi m hat, you add to it some correction term, and psi m f is subtract the same correction term. So the left-hand side will have no correction term. It will remain a meromorphic Jacobi form. And that's, I think, the reason why the Appel-Lerch sum played a role in this development. So actually, maybe I can say it here. Yeah. So here, so the shadows in the black hole problem and in all of Ramanujan's examples are actually particularly simple. And they themselves are given by this theta function that I introduced earlier. So I should probably hurry up a little bit. So for the vector valued modular forms, basically the shadow is the theta function. So shadow, the holomorphic anomaly is theta ml tau bar. And therefore, for the Jacobi form, you get this nice expansion, theta bar theta. And then there is a very interesting question of, given the shadow, what is the optimal Mach modular form? Because as I told you, the holomorphic anomaly equation doesn't determine the holomorphic part, because you can always add to it something holomorphic. But you can ask the question, suppose I add to it objects such that the Fourier coefficients grow as slowly as possible. I mean, that's the kind of thing that mathematicians like. I mean, Ramanujan and so on, they were interested in objects which are well behaved at the cusps. So if you get objects whose Fourier coefficients and the behavior at the cusp is related to how fast the Fourier coefficients grow. I mean, this we know very well from the Cardy formula. That if you have a pole at q equal to 0, then that corresponds to the exponential growth related to the black hole counting, black hole entropy. But otherwise, if it is a cusp form, then the Fourier coefficients grow very slowly. So you can ask, what are the optimal Mach modular forms? And this is actually a very interesting story, but I will tell you just one particularly interesting optimal Mach modular form, and this is the Zagier Mach modular form. So consider the special case of m equal to 1. Then the statement is that the following objects are Mach modular forms of weight 3/2 with the desired shadow expected from the holomorphic anomaly. So you just take in this equation m is equal to 1, and you ask what is, L can therefore take two values, 0 and 1. And I want to construct an object HL of tau, which when you take the derivative, it gives me this theta function. and it should have modular properties. The non-trivial thing is, of course, it should have a modular properties. And there is a very beautiful such function, and that is this h0 of tau and h1 of tau. And the holomorphic part is given by these integers h4n, these numbers h4n and h4n minus 1. And then there is this famous incomplete gamma function. And the main property of the incomplete gamma function, like for the error function, is that if you take a derivative, you'll get something simple. You'll get a Gaussian, right? Like if you take a derivative of the incomplete error function, which goes from x to infinity, e to the minus x squared, you will get an exponential of e to the minus x. And that's what you require to get a theta function. So the reason why the incomplete gamma functions appear here is that their derivative basically gives you Gaussians, and the Gaussians are what appear in these theta functions. So Gaussians of n square, Gaussians of n square appear naturally, and that's why these incomplete gamma functions appear here. And these functions, these numbers h, are some very beautiful numbers in number theory, which we don't need to. They are defined by, as some Hurwitz-Kronecker class numbers. There is a whole mathematics which is quite interesting, but let me skip that part. So this posed another problem for me. As I'm just trying to show you that just following the logic of black hole problem, you're automatically led into this mathematics, because if you try to solve meromorphy, you're led to decomposition. Now the question becomes, the Fourier coefficients of the mock Jacobi form are unambiguously defined, and they count the horizon degrees of freedom of a single-centered black hole. Now, as we know, in many contexts, the black hole can be thought of as a left-moving excitation of an effective black string, which is the MSW string. And from the near horizon ADS3 holography, one would expect SL2Z modular symmetry. So it is natural to identify our object psi m hat with the elliptic genus of the boundary theory that exhibits this symmetry. And then you would ask the question, why is it non-holomorphic? Because I gave you this argument that elliptic genus of a conformal field theory should be holomorphic. So that raises the fourth puzzle. Why is it the elliptic genus non-holomorphic? And that's where now we will make contact with various other things, and I will rush now. For a compact SCFT, it's the elliptic genus is independent of tau bar by the standard argument. However, this can fail, this naive argument of Witten can fail if there is a continuum of states. Because if you have a continuum of states, then you cannot say that a bosonic and fermionic state cancels in pairs, because the density of states of bosons and the density of states of fermions may not be exactly equal, and they may not exactly cancel. And that is actually the source of this non-holomorphy. So very simple physical interpretation of this non-holomorphy is that because you have a non-compact theory, Witten's naive argument fails because there is a continuum of states, and you can therefore relate that to the. So let me just take a very simple example, a simple problem of supersymmetric quantum mechanics. And this was actually posed as an interesting problem by Atish. So as you know, Witten gave a very nice supersymmetric quantum mechanical interpretation of the index theorems. So the Witten index is defined as trace minus 1 to the f of e to the minus beta h of some supersymmetric quantum mechanics, where say q becomes the Dirac operator and h is the Dirac operator square, which is the Hamiltonian. And if x is compact, then the spectrum is discrete of the Hamiltonian. And the Witten index is independent of beta, this parameter beta, the temperature, the inverse temperature. And therefore, it is equal to just the ground states indexed, so n plus minus n minus. However, if you have a non-compact manifold, like a cylindrical product form at infinity, then the spectrum of the Hamiltonian is no longer discrete, and the Witten index has to be defined more carefully, including the continuum of scattering states. And this you can do using some Gelfand triplet. I mean, you have to define it carefully because it's not trace class and so on, but you can define it using some notion of a trace. And the Bose-Fermi cancellation from the continuum is now no longer exact. And therefore, the Witten index actually will have a beta dependence, even though naively you would have thought that it is beta independent. And that is the source of the tau bar dependence that we encounter in this problem, because tau bar was the right moving temperature, and that argument of Witten for the right moving conformal field theory fails, and you are left with a tau bar dependence. But a simpler version is just the Witten index of a quantum mechanical problem where the beta dependence will not disappear. And this fact was actually known to was observed in a number of cases. And actually this led us to, it gives you a nice new proof of APS theorem. And actually Atiyah had posed this as an interesting problem, that how do you use the supersymmetric quantum mechanics methods to prove the Atiyah-Singer-Patodi index theorem. And it turns out that you can actually prove the Atiyah-Singer-Patodi index theorem using supersymmetric quantum mechanics, but using what I will describe now. So for example, in this problem, the Dirac operator equation is like that. And you have some complete set of states for the boundary operator B. And so therefore you can, if you, near the boundary, you have a decomposition that the coordinate along the cylinder is U, and then the boundary can be some three-dimensional manifold, or suppose you have a four-dimensional manifold to begin with, then the boundary can be a three-dimensional manifold times R plus, or in this particular case, it's a one-dimensional manifold times R plus. And now you can look at the scattering states because you have a continuum. So Atiyah-Singer-Patodi, you were interested in defining the index for a manifold with a boundary. And in their classic paper, they related that problem to a manifold without a boundary. And that is how our non-compact Mach modular story will make connection with Atiyah-Singer-Patodi theorem, that once you are in the non-compact world, then there is no guarantee that the beta dependence of the Newton index will disappear. And that actually leads to the small correction that Atiyah-Patodi-Singer discovered, which is the eta invariant. So it makes a connection between the eta invariant and the Mach modularity in the following way. Now you have to, if you have a continuum problem, you have to calculate the density of states of bosons and fermions. So as I told you, the beta dependence comes from this lack of cancellation. And if you don't remember your quantum mechanics, but just to remind you, roughly speaking, you can determine the density of states from the phase shifts by doing some scattering. And it's given by this formula, that the difference in the density of states is given by a derivative of the phase shifts. So you think of it as an S matrix calculation. You're sending in a wave and it comes back bounced off. And it's very easy to calculate using the fact that it's a supersymmetric problem, plugging into this equation, the difference in the phase shifts and therefore the difference in the density of states. And it has this very simple formula. And if you plug it in, what you find is that the Witten index has a contribution coming from the continuum of states. And the difference, see, if you take beta going to infinity, which is the zero temperature limit, you should get n plus minus n minus, which is the index that you're interested in computing. And Witten's usual argument was that it doesn't matter whether you compute it at W of infinity or W of zero. And that is how you prove the Atiyah-Singer index theorem, that you define the Atiyah-Singer index theorem as W of infinity, but then you compute it as W of zero using heat kernel expansion. But you make a mistake because W of zero is no longer W of infinity, and the difference is given by this. Once again, the incomplete gamma function or the error function appears here. And that's why, and this is exactly nothing but the eta invariant of the boundary manifold. And the error function is related to the incomplete gamma function. And this is nothing but some regularized version of the Atiyah-Singer-Patodi, Atiyah-Patodi-Singer eta invariant. So the fact that the incomplete gamma function appears in the Mach modular story and the Atiyah-Patodi-Singer story is all traced back to the non-compactness of your problem and to the fact that the continuum states do not cancel in pairs. And the difference in their density of states is related to this incomplete gamma function. So using this, you can actually prove the APS theorem. You can give a new proof of APS theorem using sort of physics methods of scattering theory. So this was the content of my paper with my student Diksha and Arnab, postdoc. Okay, now let me come in the remaining minutes, 5-6 minutes, sorry. So I had, this is actually a very interesting story. This is our latest paper, a puzzle with S duality. So once again here, if you take del Z by del tau bar, you expect it to be zero. You expect it to be holomorphic. And a classic example of that is that if you take the Waffa-Witten partition function for n equal to 4 superangles theory on K3, then you get a partition function which is eta to the 24. And actually Waffa-Witten kind of presciently remarked in that paper that it's amazing that why does the bosonic string appear here, the heterotic string appear here, the left moving heterotic string appear here. And now from a modern perspective, you understand this, that the Waffa-Witten partition function is basically a 4-brane wrapping a K3. And the instantons are 0 branes dissolved in this. So you're computing D0, D4 bound states, and which by type 2A heterotic duality is related to the winding momenta, which are counted by this eta function. So this was a very striking strong coupling test of S duality and precursor of string-string duality. But now if you repeat the same calculation for CP2, you run into this problem. And in fact, you encounter exactly this Zagier mock modular forms that we had encountered before. And therefore, we know that the partition function is no longer modular. And so what is going on? And the answer has to do with the fact that, okay, I was going to remind you about what is the topological twist. But one way to think about the topological twisted theories, which is what the Waffa-Witten theory from a modern point of view, is that you're sort of think in terms of an M5 brane. If you take an M5 brane, then its transverse directions give you the R symmetry. So if you take, for example, M5 brane in 11 dimensions, the transverse symmetry is R5, and that gives you, that gives you the SO5 symmetry. You could take that M5 brane wrapping X times T2, and then again you will have SO5 R symmetry. But now if you replace this R5 by some other manifold, then that corresponds to identifying some of the symmetries, the R symmetry with the rotation symmetries. And that is basically corresponds to doing the topological twisting. So you can actually realize the topological twist very simply geometrically by considering an M5 brane on X cross T2, where X is the 4 manifold in which you're computing. It can be K3 or CP2. And not R5, but it can be some other manifold. In this case, for example, you can take the omega 2 plus X, which is like the self-dual 2 forms of X, the space of space self-dual 2 forms of X. So that gives you additional 3 directions times R2. Because, okay, so now, as we know from our modern perspective, the whole story of, say, the AGT story and so on is that you can now consider whether X to be small or the T2 to be small. And you will get 2 pictures of the M5 brane, which will look either 4-dimensional or the 2-dimensional. So you have a 6-dimensional M5 brane theory, which you don't know what it is. But if you compactify it on a T2, you'll get a 4-dimensional angles theory. If you compactify it on X, you'll get a 2-dimensional. And we can basically analyze it in both these pictures, either as a 2-dimensional sigma model or as a 4-dimensional gauge theory. And let me just very briefly describe the 2-dimensional sigma model. If you consider we are interested in SU2 gauge theory. So there are 2 separated M5 branes, and their relative motion, we can obtain a sigma model by usual KK reduction of the tensor multiplet. And the bosonic fields are 5 scalars plus a self-dual B plus. And but now if you have a twisted theory, then the bosonic fields are 3 bosons corresponding to transverse motions in R3, and 1 right moving boson coming from this B field. And that right moving boson has a SU2 radius. It has the gauge symmetry is determined by the fact that when the M5 branes are on top of each other, you have SU2 gauge theory. So that determines the radius of that boson. So the total content of this theory is that you have 3 non-compact bosons on a circle mod Z2 at infinity. This is far away from when the M5 branes are far away from each other. And this theory has a free, it has a 0,1 supersymmetry. And there is a free action, but there is a Wess-Zumino term. And that can be actually traced back to this very nice paper of Ganor, Matrol, and Ken, interrogated in 20 years ago. That the M5 it's like a topological West-Zumino half term on the 6 brane world volume theory, which you can sort of determine by some anomaly considerations. And because of that, when you compute when you try to compute now the holomorphic anomaly equation, you pick up a boundary term, because usually the way you argue it is that del z by del tau bar is q of something, and q you interpret as a de Rham operator in some field space. So it looks like an integral of a closed form. But when you use Stokes' theorem, you can pick up a boundary term if your space is non-compact. And the boundary term is basically, you can show, it was as was argued by Gayotto and Johnson-Fried, that it's basically an expectation value of the supercurrent in the boundary theory. And that's actually very easy to calculate. And because of this topological term, the supercurrent is no longer of the free theory, which would have been just psi I del xi, but it has a 3 fermion term coming from the West-Zumino term. And that is enough to soak up, because you had 3 bosons and 3 fermions in the boundary theory. And you would have gotten a 0 answer if you were careless. But because there are 3 fermions and in your insertion operator, they soak up the 0 modes and you get a non-zero answer. And so you can understand all these operators, all the answers that appeared in the Waffa-Witten theory very nicely. The factor of 3 comes from the fact that you have a quantum of H flux. The eta to the tau to the -3 comes from the fact that you had 3 left moving bosons. The anti-holomorphic theta function that appears, which is the shadow, is basically the right moving momenta of the compact chiral boson, the radius square root of 2. And the factor of tau 2 to the -3/2 comes from the integral of the 0 modes. So we can understand the Waffa-Witten equation completely, which they had, just gotten from some mathematical results without a physical explanation. There is a very similar and very beautiful gauge theory calculation, because just if you are going on the Coulomb branch in the gauge theory, then naively again you would see that there are too many fermionic 0 modes, and if you take the del by del tau bar derivative, it would vanish. But once again, because of a Truft anomaly matching and so on, there is a West-Zumino term and corresponding to it, which is related to by supersymmetry to a Dine-Seiberg term, which ultimately is related to the 6-dimensional half West-Zumino term of Kahn and others. And if you take that into account on the Coulomb branch and you do your calculation correctly, again the 0 modes are soaked up. And in the gauge theory regime, the factor of 3 comes from the first Chern class of the canonical line bundle of CP2. The factor of eta tau to the -3 comes from the contribution of point-like instantons. The theta functions comes from abelian anti-instantons. And tau 2 to the -1/2 actually comes, it's a fairly complicated calculation using some auxiliary off-shell formulation. It comes from an integral over the constant mode of the auxiliary field. But once again, you can understand essentially everything. I mean, somehow the normalizations are not completely fixed in this picture, but other than that, you get everything. So I will stop here. So it's not, of course, from the modern perspective, you are recovering the fact that the 6-dimensional M5 brane really knows everything. And the 4D picture and the sigma model picture are related to each other because they're lifted to the 6D theory. So even though this surprising fact that these two answers agree from a modern perspective is not surprising. But what is surprising is the appearance of mock modularity. And, you know, I sort of got into it by accident, but it led to all kinds of interesting things. And I think now it's clear that mock modularity is going to occupy a kind of a position in our understanding of physics, because after all, non-compact conformal field theories are all over the place. And in all these contexts, or in contexts like Atiyah-Singer-Patodi theorem, from the topological point of view, there will be some hidden mock modularity, sort of hidden modularity or the mock modularity in the problem. So I will end by this picture of Ramanujan. Okay.
Thank you, Atish, for the wonderful talk. Let's see, there were some questions in chat. Arnav?
Hi. Yeah, so one of the questions in chat was actually directed to the chat, but I was wondering if the dive read results are theorem, which I don't know in great detail, but my understanding was it was kind of the Theta invariants when you go down one dimension further. But those eventually give rise to depth 2 modular objects.
Yes, I think the connection with Diophrid theorem is very interesting, and it's something that we should explore. Yeah, we are sort of, yeah, I don't have anything very concrete to say about that. Yeah, but I think, yeah, I don't have something very specific to say about it. But I think it's an interesting problem which is closely related.
Okay, so maybe I could ask a more general question, which is, could you say something analogous to what you said in the talk about higher depth modular objects?
Yes, so higher depth Mach modular forms appear, for example, very naturally if you take SUN gauge theory instead of SU2 gauge theory. And I think this is some work also with Boris and collaborators, and also Greg and Jan Manschott and collaborators, and earlier papers of Wafa, and they had encountered this. Of course, you know, some of these, these derivations were using dualities and so on. So here what we have given is a kind of a completely gauge theory derivation of the, so we can give a completely gauge theory derivation now for higher depth Mach modular forms. But there are other stringy derivations or stringy arguments for the appearance of these objects, you know, in earlier literature. And they appear very naturally in SUN gauge theories. Maybe Boris wants to say something about this. He might have something to say about this.
They also appear in in n equal to 2 supersymmetry when you have multi-center configurations with more than just 2 centers.
Yes. Okay. Yeah, so in the n equal to 4 story, they appear in SUN. And the way they appear is that you can sort of think of SUN as SUN1 cross, you break it first to SUN1 cross SUN2. And then you repeat this, you do some kind of a recursion. And that's how the higher depth ones occur in that problem.
Okay.
Are there other questions? No questions?
It's hard to.
Great. Well, let's thank Atish again for the very nice and clear talk.
Yeah, thank you. Thank you, Ken.
Thank you.